So this is what I call a local gravity problem. You'll also see it worded on the homework and on quizzes and on tests and in your book as find g on this planet or find the acceleration due to gravity. They're all synonymous. Local gravity, finding g, etc. They're all synonymous. And the two equations that I recommend you always start with are just write down force weight equals mg and write down F sub g is equal to g capital M lowercase m over r squared. And capital M and lowercase m are understood to be exactly the same as m1 and m2. Now I'm going to combine these two and you get mg is equal to g capital M lowercase m over r squared. This lowercase m really is the same mass, so those cancel. And now we're just going to plug in for g. But we do have to make a little bit of a modification. Our mass of the planet is in units that we want. Kilograms are the standard units in physics. But the radius of the planet, this radius, I'm going to rewrite it as 267,000, and I'm adding 3 more zeros to convert it to meters. So it's 267 million meters. That's the radius. Careful, if I give you the diameter of a planet, and when you look up planets in tables, they're often given as a diameter, then you're obviously going to cut that in half. Okay, so careful. You definitely need this to be in meters. Remember that the standard units in physics are kilograms, meters, and seconds. All right, the standard units in physics are kilograms, meters, and seconds. So now I simply plug in, and I'm not going to write those numbers in. I'm just going to go over here and indicate that this is what we're trying to find. This is known. It's 6.67 times 10 to the negative 11th. I'll write that one over here. G is 6.67 times 10 to the negative 11th. And it's got those ugly units of Newton meters squared per kilograms squared. And I ran out of room there, but it's Newton meters squared per kilograms squared. You're going to plug in. Don't forget to square the r. And you're going to end up with the acceleration due to gravity on this planet. Notice, you were not given the mass of the object. There was no mention of the object. In this case, I threw in this astronaut. I threw in this astronaut in this case. But it's any object on the surface of that planet will have that acceleration. Okay, so now we're going to crank out a number. Did anybody already do that? Go ahead. 0.42. Okay, that sounds familiar. I did this problem before. And what are my units going to be? Meters per second squared. This is an acceleration due to gravity. Question that was just asked is, what about capital M? We do know capital M. It's this value here. And I neglected to check off R as well, and that's this value here. So we really did know all those values, and we plug in and we get 0.42 meters per second squared. So a conceptual question that might be asked would be something like, what are the variables that affect the acceleration due to gravity on another planet? And you would say that it was the radius of the planet or the size of the planet that matters, and you would say the mass of the planet matters, but the mass of the object doesn't matter. Just like on Earth, the acceleration is always 9.8 meters per second squared toward the center of the Earth, regardless of the mass of the object.